Preparing for a Java interview and bored of repetitive, dry questions? Don't worry, this video is here to help you out in the best way possible.
Whether you're a complete fresher or an experienced developer brushing up your skills, this video will crack open core Java concepts with clarity, real-life examples, and questions that actually get asked in interviews. In the next few minutes, you're going to discover how to confidently tackle core Java questions.
Okay, let's unpack this. Have you ever wondered what makes the digital world tick? Or perhaps how the applications you use every single day are truly built, beneath the surface? Today, we're embarking on a fascinating deep dive into the very core of one of the most foundational programming languages out there, Java. And even if you're not a seasoned developer, understanding these core concepts provides those incredible aha moments about how software actually works. It's really for anyone who's just, a picture of a field that underpins so much of our modern world. Our mission today is to kind of extract the most important nuggets of knowledge from a truly insightful collection of core Java interview questions. We're going to try and turn what could be dense, intricate technical talk into clear, digestible insights tailored just for you.
And what's truly fascinating here, I think, is how these seemingly straightforward interview questions actually peel back the layers. They reveal the fundamental principles and the deep-seated design philosophies that have made Java not just powerful, but truly pervasive. It's everywhere in technology. Understanding these isn't merely about ticking boxes for an interview. It's absolutely key to truly grasping the why behind the code that drives so much of our digital infrastructure. These aren't just isolated pieces of trivia. They are deeply rooted in how Java was meticulously designed right from the start to address and solve real-world complex computing challenges.
Indeed. So let's kick things off with a question that is absolutely foundational to Java's entire identity. It's about that promise that really revolutionized software development. What exactly is Java? And why is its famous mantra, write once, run anywhere, such a profoundly big deal? It almost sounds too good to be true when you first hear it, doesn't it?
It does sound a bit like computing magic, yeah. But it's actually the result of a very clever and forward-thinking architectural design. To really appreciate Java's innovation, we probably need a brief historical detour, just quickly. Historically, if you wrote a program in a language like, say, C or C++, or once you had your source code, you'd compile that program directly into machine code.
Right, the ones and zeros the computer understands.
Exactly, and this machine code is highly specific. It's intrinsically tied to the particular operating system, be it Windows, Mac OS, or Linux, and often even the specific hardware, like x86 or ARM. So this meant if you developed a C++ application and wanted it to run for Windows users and Mac users and Linux users,
you'd have to compile it separately for each one.
Literally, yes. 3 separate times, maybe more, creating distinct executables for each specific platform. And each of those versions would only work on its designated platform. This need for platform-specific compilation, it was a significant logistical and development hurdle, a real pain for programmers and companies trying to distribute software broadly without tons of extra effort and maintenance overhead.
So Java comes along and essentially says, hold my coffee, we're going to fundamentally fix this problem, make software development and distribution way more efficient. How did it manage that? What's the secret sauce that truly enabled this write once, run anywhere idea?
Well, the ingenious secret lies in a two-part system. It involves something called bytecode and the Pivotal Java Virtual Machine, or JVM. When a Java developer writes their source code, those are the Java files we typically see. They don't compile it directly into machine code for a specific OS, like with C++. Instead, a specialized Java compiler, it's called JAVAC, converts your .java file into an intermediate language. And this intermediate language is what we call bytecode. It's essentially platform independent. It's a set of instructions that no physical computer or CPU can directly understand, not on its own.
Like a universal blueprint.
Exactly, like a universal blueprint describing the program's logic. This bytecode is then neatly stored in .class files.
Okay, so if this bytecode isn't machine code, how does the computer actually execute the program? That's where the magic of the JVM truly comes into play, right?
Precisely. The JVM is the absolutely crucial component here. It orchestrates Java's platform independence. And it's not just one thing. There are different implementations of the JVM, carefully tailored for each specific operating system and its hardware. So you have one for Windows, a distinct one for Linux, another for Mac OS, and so on. When you decide to run a Java program, the JVM installed on your specific system takes that platform-independent bytecode from the .class file and dynamically translates or interprets it into the specific machine code that your particular operating system can understand and execute. This translation happens right then, in real time.
Ah, I see the brilliance now. That makes it incredibly clear. It's like, okay, think of bytecode like a universal language, maybe Esperanto.
That's it.
And then the JVM is like a highly specialized translator specific to each country, or operating system in this case. That dedicated translator lets the universal language be perfectly understood and acted on by the locals, the machine itself. So a developer writes their code just once, compiles it into this universal bytecode, and then remarkably, that same bytecode can run consistently on any system that has the correct JVM installed.
That's incredibly powerful and elegant. You've nailed it. That's a perfect explanation. And this architectural design also introduces us to two fundamental components. They form the backbone of the Java ecosystem. First, we have the JRE, or Java Runtime Environment. This is the package you typically need if all you want to do is run existing Java applications. The JRE includes the JVM itself, plus a whole set of core Java libraries that applications rely on. So looking at the bigger picture, the JRE is what really enables Java's ubiquity. If you just want to use a Java app, maybe an enterprise client, a web app, whatever, you just need this essential package installed.
And then for folks actually building these apps, the developers, they need something more, right? That's where the JDK comes in.
That's right. The JDK, or Java Development Kit, that's the complete suite developers use to develop, compile, and debug Java applications. It's a true superset of the JRE. It includes everything the JRE has, the JVM, all the core libraries, plus a collection of indispensable development tools.
Like the compiler.
Exactly. Tools like the Java compiler, which, as we said, turns source code into bytecode. Also a debugger for finding errors and various other utilities critical for writing, testing, and packaging Java programs. So, yeah, if you're writing Java code, you need the JDK. If you're just using Java apps, the JRE is enough.
That distinction makes perfect sense, vital for anyone working with Java. Now, a question that always comes up, especially with interpreted languages, is performance. If the JVM is mostly interpreting bytecode, isn't that inherently slower than just running machine code that's been natively compiled beforehand?
That's a very perceptive question, a common one. And it's exactly where modern JVMs show how sophisticated they've become. You're right that initially, when a Java program starts up, the JVM does act a bit like an interpreter. It translates bytecode line by line, instruction by instruction, and yeah, that step-by-step translation can add some overhead. It might make things seem slower at first compared to fully precompiled native apps. However, to really combat this potential bottleneck, modern JVMs include a highly advanced component. It's called the just-in-time, or JIT, compiler, and this directly addresses that important question. If the JVM interprets, isn't it slow? Well, the JIT compiler is the answer. It bridges that gap.
Ah, the JIT compiler. I remember hearing about that, how it boosts Java's speed. How does it actually work? What's it doing under the hood to optimize things?
The JIT compiler is incredibly clever, really. It's basically an adaptive optimizer. It constantly watches the running Java program. It dynamically identifies what are known as hotspots.
Hotspots.
Yeah, these are sections of bytecode that get executed really, really frequently. Think of like loops that run millions of times or methods called over and over again. When the JIT finds these hotspots, it takes those specific sections of bytecode and right there on the fly, compiles them into highly optimized native machine code.
While the program is still running.
Exactly, while it's running. This newly compiled machine code is then cached, and it gets reused every time that hotspot is hit again. This process significantly speeds up the most critical parts of your application. Plus, modern JITs use all sorts of other advanced tricks.
Like what?
Oh, things like method inlining, basically pasting small common methods directly into the caller's code to skip the call overhead, or loop unrolling, even fancy stuff like escape analysis to optimize memory allocation. They're constantly profiling and adapting improving performance as the application runs.
So it's like the JVM starts as a general translator, interpreting everything, but then for the really common phrases or crucial parts of the conversation, it learns to speak the local language perfectly. It optimizes and compiles those bits into native code for super fast execution. That's brilliant. It's like a learning optimizer.
Precisely. This JIT compilation really bridges the gap. You get the flexibility of interpretation, the write once, run anywhere, but also the raw speed of native code for the parts that matter most. What this means in practice is that modern Java applications can often achieve performance that's comparable to, and sometimes even better than, directly compiled languages like C++ Extra, especially for long-running server applications where the JIT has lots of time to work its magic. It really shows how smart architecture can solve tricky trade-offs.
So what does this whole architecture discussion mean for you, our listener? It means developers can write their code once. Just once. And that exact same code will run consistently, predictably, across different systems like Windows, Mac, Linux, without needing changes. That's a huge efficiency win for developers. Massive. And maybe more importantly for users, it ensures the apps you use every day behave reliably no matter what computer you're on. This whole setup source code to bytecode interpreted and optimized by the JVM, the JIT jumping in on hotspots, that's the absolute core of Java's write once, run anywhere philosophy. It's truly a cornerstone of modern software development. Now, let's pivot slightly. From the JVM's architecture to something fundamental that pretty much every Java program uses constantly, often without thinking about it, string objects. And here's where it gets really interesting for something we use all the time. Why are string objects in Java designed to be immutable? This isn't just some random choice. It's foundational. It has huge implications.
That's an excellent question. It takes us right into one of Java's most critical design principles for a data type we see everywhere. When we say a string object in Java is immutable, what we mean is this. Once a string object is created with a value, its content, its value can never be changed. Any operation that looks like it's modifying a string, say concatenating two strings using concat, or trying to replace a character, what it actually does is create an entirely new string object in memory.
A brand new one?
A brand new one, yes. The original string object itself, it remains completely untouched, unchanged in memory.
Okay, so if I have string greeting hello, and then later I do greeting.concat world, I'm not actually changing the original hello string itself. What's really happening is a brand new string hello world gets created somewhere else in memory, and my greeting variable just gets updated to point to that new string. The original hello is still floating around until the garbage collector cleans it up. Maybe, is that right?
That's a perfect and very accurate way to visualize it. Exactly right. And the why behind this immutability, it's multifaceted. It provides a whole host of significant benefits. Benefits that often work silently in the background, but are absolutely crucial for Java's robustness, security, and performance.
Let's unpack those benefits because they really explain why this design decision was made. Let's start with security. How does making strings unchangeable help make Java apps more secure?
Security is huge, especially for a language like Java that's used so much in network programming, big enterprise apps, critical systems, places where data integrity and preventing malicious manipulation are non-negotiable. If we connect this to secure programming practices, think about how often sensitive stuff gets passed around as string arguments. Things like file paths, network addresses, user authentication tokens, database connection details.
Right, critical information.
Exactly. Now, if string objects could be changed, if they were mutable, imagine a malicious program, or even just buggy code, altering the content of a string after it's been checked for security. For example, maybe some code carefully validates a file path, make sure it's safe. But if that string could be changed after the check,
it could be made to point somewhere dangerous, like a system file.
Precisely, leading to a serious security hole, like reading files it shouldn't or corrupting data. Immutability completely eliminates this risk. Once that sensitive info is in a string and validated, you know it can't be tampered with later by some other part of the program or another thread. Its integrity is guaranteed.
That's a massive benefit. It's like signing a contract once signed. You trust the terms won't be secretly changed. Okay, next up, thread safety. How does immutability help when multiple parts of your program are running at the same time?
This is another huge advantage. In multi-threaded programs where multiple threads might try to access and maybe change the same shared data simultaneously, you usually have to deal with complex synchronization. Things like locks, mutexes.
Yeah, that stuff gets complicated fast.
It really does. It's needed to prevent data corruption, race conditions, inconsistent states. But immutable objects, by their very nature, are inherently thread-safe. Because their internal state never changes once created, multiple threads can safely read them at the same time without any risk. There's zero chance of one thread messing up the string while another thread is reading it. This totally eliminates that possibility of inconsistent data from concurrent access, which means fewer headaches for developers trying to manage multiple tasks at once. String just works reliably without needing explicit locks or complex concurrency controls. It simplifies a notoriously tricky part of programming.
So it inherently makes concurrency easier, which, yeah, is often a major source of bugs. That's a definite win. What about performance? How does an unchanging string actually make things faster sometimes?
Performance gains often come from something called hash code caching. The hash code method computes a numerical hash value for an object, right?
Used in hash maps and things like that.
Exactly. It's used all the time for string objects, especially when they're keys in hash-based collections like hashmap or hashset. Since a string is guaranteed immutable, its content never changes. Its hash code can be calculated just once, right when the object is created, and then that value can be stored or cached for the entire life of the object. This avoids recalculating the hash code every single time it's needed, which saves a lot of processing time, especially in apps that heavily use hash maps for quick lookups. What's fascinating here is how this simple design choice immutability can have such a big positive impact on performance, especially for something as fundamental as using strings as keys in data structures.
That's really clever. It's like pre-calculating a complex math answer because, absolutely know the inputs will never change. Elegant.
Precisely. And there's one more security aspect, often overlooked, related to how the JVM loads classes internally. The Java.lang string class isn't just for developers. It's fundamental to the JVM itself. The JVM uses strings for crucial internal operations, like loading classes dynamically, managing file paths for code. Ensuring the absolute integrity of these internal string values is critical for the JVM's own security and stability. If core strings used for things like class names could be altered after being checked, the JVM itself could potentially be compromised. Immutability acts as a safeguard against that kind of internal tampering.
And just briefly, are there memory benefits too? Does immutability help with how memory is used?
Yes, absolutely.
Yeah.
Immutability makes a key memory optimization called the string pool possible and safe. The JVM keeps a special area in memory, the string pool. When you create string literals in your code, like string as hello, the JVM first checks if an identical string already exists in this pool.
Oh, so it checks if it's seen hello before.
Exactly. If it finds a match, instead of creating a new string object, it just gives you back a reference to the existing one in the pool. If there's no match, it creates a new one and adds it to the pool. Immutability is what makes this safe and efficient. You can safely share references to the same string from the pool across your code because you know nobody can change it and mess things up for everyone else sharing it. This saves a lot of memory by avoiding duplicate string objects.
So, summing it up, string immutability in Java isn't just a minor detail. It's a core design choice with huge positive effects on security, concurrency, performance, and even memory usage. It really underpins Java's reputation for being robust and reliable, especially in big applications. Sometimes preventing change is the most powerful design choice. Building on that idea of fundamental design.
That's it for part 1 of our Core Java interview series. Check the keynotes in the description for quick revision. In the next part, we'll cover marker interfaces, method overloading, the static keyword, and more. If this video helped, don't forget to like, subscribe, and stay tuned for part 2. Thanks for watching.